morning viewers. Today we will be discussing solution of system of equations. We will be starting with m equations in n unknowns x1, x2, xn. These are m equations which are linear. This can be represented by a matrix equation Ax is equal to b, where the matrix A is m by n coefficient matrix and the x is the column vector of unknowns consisting of x1, x2, x3, xn, and b is the column vector of known values which appear on the right hand side of this system of equations. The coefficient matrix Aij is m by n matrix having a11, a12, a1n in the first row, and the last row is corresponding to the last equation am1, am2, amn. As I told, x is the matrix of unknowns consisting of x1, x2, xn, while b is column vector of known values b1, b2, bm. This system of equations is homogeneous system. If all bi's are 0, if all of these are 0, then we have a system of homogeneous equations, or we call it a homogeneous system. But if any one of them is non-zero, or at least one of them is non-zero, then the system is a non-homogeneous system. We will define an augmented matrix associated with the given system Ax is equal to b, and it is given as this C. You may notice that this equation has n plus 1 columns. These n columns are the same as the coefficient matrix, and this is the right hand side. Now, this is a convenient way of expressing the equation in a compact form. The system of equation is written in this compact form. We know many methods to solve the system of equations, especially when we have 3 or 4 equations. So, if we apply this elimination method for a system of 3 equations in 3 unknowns, then one can multiply the second equation by 3 and subtract it from 1, and the third equation is multiplied by 2 and subtract from 1. The idea is that we first eliminate x from the remaining 2 equations, and what we have is a system of 2 equations in 2 unknowns. So, if we do this simplification, then we can have 9y minus 4z is equal to minus 1, while this second operation gives us minus 9y plus 7z is equal to 4. Then one can add the equation number 5 and 6. This y will be eliminated, and what we have is 3z is equal to 3, which gives us z is equal to 1. Now, if you substitute z in 6, we can get y as 1 by 3, and substitution of y and z in 6 gives us x is equal to 1 by 3. In fact, substitution of y and z in 6 will be satisfied automatically, but when we substitute this value of y and z in equation 1, we will get x is equal to 1 by 3. So, this system of equation is solved. Now, we are applying this method from our school days. The idea here is that we want to extend this method so that it can be applicable to large system of equations, like in engineering problems and the real life problems. We have number of equations, number of situations where we have number of equations which are linear, but the number of equations are 10, sometimes 20, maybe 50, or maybe more than 100. So, how to extend this method so that we can conveniently get the solution of such equations, if at all the solution exists. So, now we will see how this elimination method can be generalized and applied to higher order system of equations. One may notice that the method which you have applied for system of equation, the same operations can be applied to augmented matrix. You do not have to write down x, y, z every time, you simply apply those operations on augmented matrix and the result will be the same. Now, while applying the method, we have applied number of operations. Those operations can be categorized into 3 categories. One is we have made interchanges in the rows, we have multiplication of an equation by a non-zero constant, or the third type of operation may be that addition of a constant, multiplication of one equation to another equation. So, these 3 types of equations may be used, these 3 types of operations may be used to obtain the solution of equations. Now, after that we will introduce the elementary row operations on matrices. The idea is we will not be using these operations on the system of equations, rather we will be using these operations on the augmented matrix and we will get the solution. So, correspondingly we have 3 operations. The first operation is interchange of any 2 rows. We symbolically we write Ri interchange Rj, that means the rows I and j are interchanged. The second operation is that multiplication of a row by a non-zero constant. So, if k is non-zero, then ith row is multiplied by k to give us modified ith row. And the third operation is that Ri is modified as k times Rj added into Ri. So, these are 3 different types of operations which can be performed on matrices. We call these operations as elementary row operations. We call them row operations because they are applied to rows of a matrix. Now, we can make a remark here that when augmented matrix is viewed as a representation for a system of equations, then these row operations which we have discussed are equivalent to operations 1 to 3 performed on system of equations. Now, these elementary row operations, when they are applied to identity matrix, let us say I consider I3, that is a 3 by 3 identity matrix, and I apply an operation R1 interchange R3. So, when I interchange the first row with the third, then this one will come here and this one will come here. So, when I apply this operation, then what I have is a matrix H13. So, H13 represent an elementary row matrix which is obtained by applying elementary row operation of the type where R1 is interchanged by R3. That is the significance of this 1 3. Then other row operation is that a particular row is multiplied by a constant. So, let us say we are multiplying that constant, a particular row say R3 by a constant alpha. So, if I apply this operation on identity matrix, then third row which is 0 0 1 will become 0 0 alpha. I call this matrix as H3 alpha because third row is multiplied by alpha. Here I am using only one index because only one row is affected. Then the third type of operation may be written in the form R1 goes to R1 plus alpha times R2, meaning thereby that second row is multiplied by alpha and added into first row. So, if I apply this operation on this, then second row will become 0 alpha 0. When added into this, it is 1 plus alpha and then 0. So, this operation is called H12 alpha because alpha is a constant to be multiplied by the second row and added into 1. So, we have 3 different operations H13, H3 alpha and H12 alpha. Now, these matrices are called elementary matrices. So, elementary matrices are obtained from identity matrix by applying elementary row operations. So, if I have a 2 by 3 matrix and apply an operation H13 on this matrix, then this actually is equivalent to this product where I am applying where I am multiplying H13 by the given matrix. What should be the order of the matrix? This identity matrix, this must be such that this multiplication is confirmed, it is possible. So, this on identity matrix I apply this operation, that is first row and third row are interchanged. So, we got this matrix, this multiplied by this, one can check that it has the same effect as if we are applying operation on this matrix. Let us see 0, 0 and 1. So, this becomes A3. Then if I multiply by this, I will get this element which is 0, 0 and B1. So, we will have finally this matrix as if this matrix is interchange first row and third row. So, that is the final matrix. Now, this type of operation can be done for all type of operations like H3 alpha when multiplied by this, that means we want to change this matrix, we want to apply the row operation on this matrix. So, that the third row is multiplied by alpha. So, what I do is I first apply this operation on the identity matrix. So, if third row is multiplied by alpha in the identity matrix, only this element will be affected. So, we will be having 1 1 alpha multiplied by this, and if you really perform this multiplication, what you will be having is this matrix. Similarly, H12 alpha multiplied by this means we will be having the first row plus second row multiplied by alpha. So, what is H12 alpha is this matrix multiplied by this matrix, and if you perform this multiplication we will be having this matrix. Now, we say that B is the elementary row transformation on the matrix A. So, let us say we have a matrix A, we perform elementary row transformations on the matrix. Let us say after performing the transformation what we get is B, the matrix B. Then if P is the elementary row operation on I, the same elementary row operation which you have applied on A. So, if P is the elementary row transformation on I, then B is equal to P into A. So, it is pre-multiplied by the matrix A and the result is the same. Now, this actually gives us the result that A can be obtained as P inverse P A. So, from after applying row transformation, A is transformed to B, and you again apply set of another transformations and you will come back to the original matrix A, provided this P inverse exists. So, if P is non-singular, then P inverse will exist, and in that case A can be obtained as P inverse P A. So, one can obtain from B the matrix A after applying elementary transformations. Now, what is the matrix P? P is the elementary row transformations on I. I is non-singular. After performing elementary row transformation, matrix remains non-singular, and that means P inverse exists. So, it is possible that you obtain A from the matrix B. Now, this means one has to see about the inverse transformations Hij inverse will be Hij. The idea is Hij is the transformation which interchanges ith and jth rows. So, if you want to come back to the original matrix, then you have to apply Hij inverse, that means you again interchange I and j. So, interchanging I and j twice, you will be getting the same matrix. So, that is why Hij inverse is equal to Hij. Now, Hi inverse alpha, that is the inverse of Hi alpha is Hi inverse alpha. This can be obtained as Hi times 1 upon alpha. See, if I multiply the ith row by alpha to get some matrix B, then if I want to come back to the original matrix, I have to multiply the same row, but with the constant 1 upon alpha, provided alpha is not 0. That is why I say Hi inverse alpha is equal to Hi 1 upon alpha. Then the third operation, Hij inverse alpha is equal to Hij minus alpha. This operation simply means that jth row is multiplied by alpha added into I. Now, if we want to come back to the original matrix, what I do is I multiply the jth row by minus alpha, so that the result will be the same. So, whatever row transformation has been done here, that will be nullified and we will get the original equation. So, that is how Hij minus 1 alpha is equal to Hij minus alpha. The idea is that you can perform number of operations on a elementary on a matrix. So, let us say I have been given a matrix, a 3 by 2 matrix A1 B1 A2 B2 A3 B3, and I apply 2 operations successively on this matrix. The first is R3 multiplied by R3 changes to alpha times R3, and the second operation is that R1 and R3 are interchanged. Now, these 2 successive operations can be performed on this matrix, then we will be getting this matrix. The idea is, what is this? This matrix is nothing but H3 alpha, and this matrix is nothing but H13. So, these are the elementary row operations. So, it has the same effect whether you apply these 2 operations on this matrix or you multiply these 2 matrix and then multiply it with this, the effect will be the same. So, let us see this. If you really perform these multiplications, then first this product 0, 0 and 0. So, this element is 0, 0, 0 and 0, this element is 0, 0, 0 and alpha. So, we will have first row has 0, 0 alpha. Similarly, one can perform the second row multiplied by this, we will be having 0, this multiplied by this is 1 because of this product, this multiplied by this is again 0, but this row multiplied by this row is 1, 1 multiplied by 1, this is 1, 0 multiplied by 0, 0 multiplied by 0. So, the result is 1 here. Then this row multiplied by second row is 0 and third row multiplied by third column is again 0. So, product of these 2 matrices, elementary matrices, comes out to be this, and when you apply this product to this, what we will be having is this matrix. So, let us first check this element, it is 0, this, and alpha times A3 is the only non-zero element, rest of them will be 0, and this multiplied by this will give me alpha B3 as this element. When we multiply second row by this will be 0, this will be A2 and nothing will be contributed from this product. So, we will have only A2. Similarly, when you multiply this by this, we will be having A1. So, what we are having is A1. So, the idea is when we apply these 2 operations successively, we will have this matrix. This can be obtained directly applying to this, or you apply series of elementary matrices. Now, this leads to a definition which says that an m by n matrix A is said to be row equivalent to an m by n matrix B if B can be obtained from A by applying a finite sequence of elementary row operations on it. So, two matrices are row equivalent if one can be obtained from another matrix by applying finite sequence of elementary row operations on it. Now, this means that we have a matrix A. On this matrix A, I apply sequence of elementary row operations. What are those operations? E1, E2, E3, En plus 1. They are multiplied, pre-multiplied on the left hand side of A. What are E1, E2, En? These are elementary matrices, that is the same row operations applied on identity matrices. So, all these matrices when multiplied together, let us say this is P. So, if B can be written as a matrix P times A, then we say B and A are row equivalent matrices. Or you say the matrix A and B are row equivalent if there exists a non-singular matrix P such that B is equal to P inverse A. Since all E1, E2, Ens they are identity matrices, and on those elementary matrices we have applied row operations. So, all these are non-singular. When they are multiplied together, they remain non-singular, and that is why this P is non-singular, and non-singular means P inverse exists. So, if you can write down B is equal to P inverse A, then A and B are row equivalent. Now, this row equivalence is actually an equivalence relation. For that we have to prove that the relationship is reflexive. By this I mean to say that every matrix is row equivalent to itself. The proof is simple. I write A is equivalent to B. This symbol is used for equivalence. So, the matrix A is equivalent to A. That means you apply the there is a matrix A, there is a matrix I which when applied to A on the left hand side will have A, the same matrix. So, A is equivalent to A. Then the relationship is symmetric. By this I mean to say if A is row equivalent to B, then B is row equivalent to A. Now, proof of this is simple, like if A is equivalent to B, then there exists a matrix P such that B is equal to P A. This is the basic definition of equivalence relationship, where P is a non-singular matrix. So, since P is non-singular, then P inverse B will be A. So, that means if you are multiplied by P inverse on both the sides of this, then this P inverse B is P inverse P multiplied by A is nothing but A. So, P inverse B is A, and if P inverse B is equal to A, that simply means that B is equivalent to A. That means we have started with A equivalence to B, and what we have is B equivalent to A. That is, if A equivalent to B, then B is also equivalent to A, and that proves the reflexive property of the operations. The third is the transitive property. It says that if A is row equivalent to B and B is row equivalent to C, then A is row equivalent to C. So, now I have three matrices. In reflexive I have one matrix which is equivalent to itself. Symmetric I have two matrices, they are equivalent to each other. Transitive I have three matrices. If A is equivalent to B and B is equivalent to C, then A is row equivalent to C. That means this is being given to us, A is equivalent to B, B is equivalent to C, and this implies that A is equivalent to C. That is the meaning of the transitive property. To prove this, let us say A is equivalent to B means B is equal to P A. That means there exists a matrix P such that B is equal to P A. Now, B equivalent to C means there exists an elementary matrix Q such that C is equal to QB. Now, if I write down B is equal to PA from here, then C is equal to QP into A. What is QP? QP is a product of elementary matrices. What is P? P is also a product of elementary matrices. What is QP? Another elementary matrix, another matrix R. So, C is equal to RA. That simply means that C is equivalent to A. So, we have proved reflexive property, we have proved symmetric property and the transitive property, and this means that row equivalence is an equivalence relation. Now, in all this discussion we are applying elementary row operations. Actually, the same way one can define elementary column operations. Elementary column operations are same operations, but they are applied to columns. The operations are two columns are interchanged, one column is multiplied by a constant, or the third type of elementary column operation is that one column is multiplied by a constant added into the another column. So, we will have three types of elementary column operations, and these are again equivalent to the column operations applied on elementary identity matrix. What we have is again an elementary matrix, but this time we call it right elementary matrix, because when we apply row operations, then elementary matrix is pre-multiplied and we get the final result. But when we apply column operations, then this elementary matrix must be multiplied on the right hand side. That is how we differentiate the two matrices. So, it is left elementary matrix as far as row operations are concerned, and we have right elementary matrix when we apply the column operations. So, we can apply elementary column operations on matrices, and one can define same equivalence relationships like the matrices A and B are column equivalent if there exists a non-singular matrix Q such that B is equal to AQ. Mind here I am multiplying on the right hand side. For a row operation it was on the left hand side. That is the basic difference between the row operations and column operations. And any this matrix Q is actually series of elementary matrices, elementary column matrices, and these are E1, E2, En. I am using small letters E1, E2, En to denote the elementary column matrices. So, Q is equal to E1, E2, En. Now, if the matrices A and B are equivalent, if there exists a non-singular matrix P and Q such that B is equal to PAQ. See, you have a matrix A and a matrix B. One can obtain matrix B by applying simply row transformations, or one can obtain a matrix B by applying column transformation, but sometimes we apply row as well as column operations from to the matrix A to get the matrix B. If there is such a situation, then we say B is P times A into Q. What is P? P is the elementary row operations and Q is the column operations. So, the two matrices are they are equivalent if B is equal to PAQ. So, we have row equivalence, we have column equivalence, and simply the two matrices are equivalent. Now, all these concepts will be used to obtain the solution of equations. Now, before I really apply these concepts to solve system of equations, I like to introduce the concept of reduced row echelon form. Now, we define a matrix M by N to be in reduced row echelon form if it satisfies certain properties. So, what are those properties? The first property is that all 0 rows, if there are any, are at the bottom of the matrix. So, matrix is in the reduced row echelon form if there are some 0 rows, then they will be at the bottom of the matrix. And the second property is that the first non-zero entry in each non-zero row is 1, and this entry is called the leading one. For example, I have this matrix consisting of 5 rows and 5 columns, 5 rows and 5 columns. There are 2 0 rows, the 4th row and 5th row, they are 0 rows, they are at the bottom of the matrix. So, this might be a candidate for row reduced form. This is according to the first property. In the second property, we say that if there is a row which is having non-zero elements, like the first row it has 2 non-zero elements, then the first element in this row has to be 1. So, this is 1 here, this element can be any value, but this has to be 1, this also has to be 1, and even the third column has non-zero element, and this also has to be 1. So, this may be a candidate for row reduced form. The next property is, if there are 2 rows having non-zero elements, that means the rows which are not consisting of entirely zeros, let us say the rows are I and I plus 1th, then the leading one of I plus 1th row is on the right of leading one of the ith row. So, this I will explain with the example. And the fourth property is that if a column has a leading one of some row, then all other entries in that column are 0. So, let us see this example. Here we are having 0 rows, these are non-zero rows, these are leading ones. Now, this is non-zero row, it has a leading one here, and this is a non-zero row, it has a leading one here. Now, this is the ith row, this is the I plus 1th row, the leading one in this row has to be on this side, and I plus 1th row will be on the right side of this leading one. Similarly, this one and this row, these 2 rows, they are having non-zero elements, and this is the leading element of this row, this is the leading element of this row, this will be on the right of this. So, this satisfies all the properties of row reduced form. So, we say this matrix is in row reduced form. Now, one may notice that this is the boundary where we have non-zero elements, rest of the elements here are zeros. Now, this pattern is a sort of staircase pattern, and that is why we call this matrix as an Equivalence matrix or a staircase matrix. So, row reduced form is, one may notice that all elements below this boundary are 0, while the non-zero elements are on the upper side of this boundary. This boundary forms a staircase pattern, and that is why we call it an Equivalence form. So, this row reduced matrix is also called in the Equivalence form. Now, many times a matrix satisfies only the first 3 properties, then the matrix is not in the row Equivalence form. This I will explain with example. Like this matrix, a 3 by 3 matrix is in row reduced Equivalence form, as it satisfies all the properties, the staircase pattern. This matrix is again row reduced form, again all 0 rows here, leading rows ones, and then all the properties are satisfied. This matrix, all zeros on the bottom of the matrix, this again is a staircase pattern. So, this is again in reduced row Equivalence form. However, this matrix is not in reduced row Equivalence form, because this is a leading one, but this value is 2. This should be the leading one in this row, but the value is 3 here. So, this is not in reduced row Equivalence form. In this case, this is all 0, the staircase pattern is still there, but if you look at this particular column. This has a leading one, but this should have all entries in the column should be 0. That is the fourth property, but this property is not satisfied. That is why it is not in reduced row echelon form. This is non-zero, this is 1. So, this is not in reduced row echelon form. The same thing is here. This particular pattern is against the form, because this is a leading one in this row, this is leading one in this row, but this leading one is on the right hand side. This should be on this side and this should be on this side, only then it will be in row reduced form. So, this is not in reduced row echelon form. Now, in this case again the pattern is there, staircase pattern is there, but this particular column makes it different than a row reduced echelon form, because this is the leading one, but this has another entry which is non-zero. So, this again is not in reduced row echelon form. So, they are not in row, but they can be in row echelon form. Okay, now we will describe a procedure to obtain an equivalent matrix in row echelon form for the given matrix. Now, this particular form is very suitable for solving system of equations. So, first we will describe a procedure through which we can reduce a given matrix in row echelon form, and then we will see how the solution can be obtained easily. So, the step 1 is that you have to first find the pivotal column, that means the column in which we have a pivotal element. Then pivotal column is the first column from left to right in which all entries are not 0, that is the meaning of pivotal column. So, first we have to find the pivotal column in the given matrix, then find out its pivot, and the next thing is interchange the pivot row with the first row, multiply this row by pivot minus 1, and finally add suitable multiples of first row to the other rows, so that all entries in the pivotal column becomes 0, and then we can apply this method to sub matrices after removing pivotal column and the row containing the pivot. Let us see this with this illustration. So, we have been given a matrix A. I call this matrix A as an augmented matrix. That means it actually represents a system of equations with this as the coefficient matrix and this on the right hand side. This is A matrix X multiplied by the column vector B. So, this is B, this is A. Now, first thing is, you may notice that this is the first element which is non-zero. So, we have to first make this pivot as 1. So, the first step is you apply R1 to R3. So, first this make this particular row here, bring this particular row here, and then R4 is R4 minus R1. So, once this becomes R1, then R4 minus R1 will make this element 0. So, if you apply these two transformations, then what we have is this matrix. So, it is 2 here, 0 0 0, this 0 0 are already there, this is been interchanged and this is subtracted from this. So, we will have this matrix. Now, then once we obtain this matrix, we write down R1 as half times R1, that makes it a pivot. So, we have this matrix. So, one may notice that only in this part there is a problem, but as far as this is concerned, this is perfectly in line with the row reduced echelon form. So, we have to make this as row reduced echelon form, and then the final result will be in row reduced form. So, that is why we now concentrate on this particular sub matrix. When we apply the same procedure here, again we find the pivotal column. So, this is the pivotal column. We apply a transformation, R4 is R4 plus R3, that will make this 0, R3 and R2 are interchanged. So, these two are interchanged, then this 2 will come here, then R2 is half of R2, so that this will become 1. So, if we apply these series of operations, we will have a matrix as this. This becomes 1 and these two will become 0. So, this we have started with the matrix. This is the leading row having 1 here. This has the leading row 1 being here. This is a pivotal element. Now, we try to apply the same procedure on this submatrix. Now, for this we first apply R4 is R4 minus 5 R3, that will make this to be 0, and then R3 is half of R3. So, this will become 1. So, if I apply these two operations, I will get the matrix as this. So, this is 2, 2 minus 17 and 14 because of this operation. Now, this again pivotal element. Now, this submatrix is to be reduced. So, I apply this operation and this operation will give me this matrix in this form. So, this is first row, first pivot, this is second pivot, this is third pivot and this is the fourth pivot, but this is not enough. It is not in row reduced form because of this non-zero element here, right. But this is in row echelon form. It is not in row reduced echelon form, it is simply row echelon form. Now, the equivalent row echelon form for a given matrix is not unique. This is the remark, because I have applied some set of transformation. You can get to a row reduced echelon form which will have different coefficients because you have applied different operations in different order. So, this form is not unique. But if you want to transform into a reduced row echelon form, then it will be unique. So, that is the basic difference between row reduced row echelon form and row reduced echelon form. Now, we have a result which says that every m by n matrix is row equivalent to a matrix in row echelon form. So, you can apply transformations so that it will reduce to in row echelon form. Another theorem says that the two systems A x is equal to B and C x is equal to D have augmented matrices A, B and C and D respectively. If matrices A, B and C, D are equivalent, then both the systems have same solutions. Now, this is an important result because you can apply different type of transformation, you may get to different type of matrices, equivalent matrices, but both of them will have the same solution. So, if AB is in row echelon form, then it is easy to solve AB because of its simpler structure and then it is equivalent to CT. So, this system is simpler and that is why it is better to reduce the system of equation into row echelon form. So, this is the basic concept behind the elimination method which we will be using. So, what we do is we consider the augmented matrix and transform into echelon form. Once it is transformed into echelon form, then we use back substitution and get the solution of the equation. Like in this case, we have been given a system of equations and these equations are this matrix is converted into this form, and from here we can apply back substitution like this in echelon form. We apply back substitution. If you consider the last equation, then x1 is 0, x2 is not contributing, x3 is not contributing, x4 is equal to 14 by 17. So, once you get x4 is equal to 14 by 17, now you apply the same theory to this, that is x1, this will not contribute, it is x3 plus 2x4 is equal to 2. From here we already obtained x4. So, we solve it for x3 and x3 comes out to be 6 by 17. So, once you solve for x4 and x3, now we form this third equation. So, x1 is not there, but x3 and x4 we have already computed. So, we can straight away get the value for x2. Then finally, we use the last equation. This is 1 x1, 2 x2, x2 is already known, 2 x3, x3 is already known, x4 is already known is equal to 1. So, we substitute in this equation and will finally get the value for x1. So, this is the solution for the given system of equations. So, the Gauss elimination procedure, this procedure was given by Gauss, this uses this concept. So, what the first step is form the augmented matrix from the given system of equations. Second step is transform A B augmented matrix to row echelon form C D by using elementary row transformation, and here we have actually used that theorem that after transforming this A B to C D in a simpler form, the solution of the two systems remains the same. So, this transformation will not affect the solution of the system, but the system will be simpler. Once we get the echelon form, row echelon form, then we use the back substitution to get the final solution. Now, it may happen that when you apply this transformation, that some of the rows becomes 0, because this is the property of echelon form, that some of the rows may be consisting of entirely zeros, then those rows can be ignored. And in fact, if there are some unknowns involved in it, then they may take any arbitrary value and the equation will still be satisfied. All those equations will still be satisfied for arbitrary values of unknowns, and the unknowns will be obtained from the non-zero elements present in the system of equations. Now, Gauss-Jordan reduction procedure is slightly a slight variation from this, in the sense that first step remains the same, that we have to form the first the augmented matrix. The step 2 is transform A B to reduce row echelon form by using elementary row transform. That is the basic difference between the two methods, Gauss-Jordan reduction procedure and the method which we have discussed just now. That method transforms the equation into row echelon form, but not reduced row echelon form. So, the idea is this will be, this matrix C D is unique in this case. In the previous case it may vary depending upon the type operations you try to apply. Then once we obtain the reduced row echelon form, then this can be used for solving system of equations. Let us see how we apply this. We apply this for the system of equations. So, the first step is to write the augmented matrix. Since the equations are 4 in number in 3 unknowns x, y and z. So, we will be getting a 4 by 4 matrix. This is the coefficient matrix and this is the right hand side. The second step is to reduce this into echelon form. So, to start with I will have to perform series of row operations. First operation is, this is already 1. So, these of the elements have to be 0. So, I apply this sequence of operations. R2 is R2 minus 2 R1, so that this becomes 0. R3 is R3 minus 3 R1, so that this becomes 0. R4 is R4 minus 3 R1, so that this becomes 0. So, if I apply these operations, then I will get to this system. After applying these operations, one may notice that only this part is to be made, this part is to be reduced. So, to reduce this part, I will first write R3 as R3 minus 2 R2, so that this becomes 0, R4 as R4 minus R2, so that this becomes 0, and then I say R2 as 1 by 3 of R2, that will make this as 1. So, applying these operations, I will come back to, I will go to this form. In this particular form, only this sub matrix is to be reduced. So, I say R3 is R3 by 10, so this become 1 and this will be 0, this will be minus 4 by 10. Now, you may notice that this is 1, but this is not 0, this also has to be 0, this also has to be 0. So, to apply this, I will say R1 is R1 plus 2 R2, so that this element will become 0. So, the result is this becomes 0 and will have this sub matrix. Now, in this sub matrix I apply R1 is R1 plus 3 R3, so that this will become 0, and R2 is R2 plus 3 R3, so that this becomes 0. So, after applying these two operations, I will be having this echelon form. In this is the coefficient matrix, this is the right hand side, will have the leading element here in the third row, all these elements 0 here, this is the second row and this is the leading one in the third row. Now, this finding the solution is straightforward in this case. This element corresponds to z, so z is equal to minus 2 by 5. This leading one corresponds to y, so y is equal to minus 11 by 5. This leading one corresponds to x, so x is equal to 4 by 5. So, once the equation is reduced into echelon form, then the finding solution is simpler. So, that is the basic difference between the first method and the second method which we have discussed. Now, number of remarks here. A linear system A x equal to b in n unknowns has no solution if a row in its equivalent reduced row echelon form has first n elements zeros, but n plus 1th element is non-zero. So, if this is a situation that all the elements in a particular row are 0 except the last one, then the system will not have any solution. Example is, let the augmented matrix AB can be reduced to the following reduced row echelon form as this. Now, may notice that this particular row has all zeros except the last column as 2. Now, this is an inconsistent system, because whatever be the values of x1, x2, xn you consider, that will not be equal to 2. So, this system will not have any solution. So, this augmented matrix has no solution, and we say such a system as inconsistent system. So, what is a consistent system? The consistent system is one which is a linear system having at least one solution. So, a linear system with at least one solution is consistent. It may have more than one solution, but one solution has to be there. An inconsistent system is a linear system with no solution. Now, if you have a homogeneous system where the right hand side has 0, then it will always has a solution, because x is equal to 0 is a solution of this equation. X is equal to 0 means all its components are 0. So, they whatever be the matrix A, Ax will be 0 in this case. So, this system will always has a solution, and that solution is a 0 solution. It may have other solutions, but it has a 0 solution, and this system will always be consistent. So, x1, x2, xn is equal to 0 will be a solution for this. So, therefore, we say that homogeneous systems are consistent. The solution in which all unknowns are 0 is called trivial solution. So, homogeneous system will always have a trivial solution, that is why it is consistent. And the solution in which all unknowns are not 0, some of them may be 0, but at least there may be one which is non-zero, then that solution is called a non-trivial solution. So, a homogeneous system always has a trivial solution. It may have a non-trivial solution or may not have a non-trivial solution. However, if we have a non-homogeneous system, then it may not have a solution. It may be inconsistent. Now, we have some results which says that if let u and v be two solutions of homogeneous system, then u plus v is a solution of the system. Then if u and v are solution of the system, then u minus v is also solution of the homogeneous system. Similarly, if u is a solution of the system, then constant r times u is also a solution of the system. Not only this, but the linear combination of u and v is also a solution of the system, that is r times u plus s times v is a solution of the homogeneous system. These properties are not true for non-homogeneous system, but these are the properties which are true for homogeneous system. Now, trivial solution is not the solution of non-homogeneous system. This is obvious because the non-homogeneous system will have at least one equation having a non-zero entry on the right hand side. So, that particular equation will not be satisfied with a trivial solution. Now, for a non-homogeneous system we have no solution also. So, now we will consider a special case where the number of unknowns and the number of equations are equal. So in that case, the coefficient matrix will become a square matrix. Now I am considering another case when we have a square matrix as the coefficient matrix and this matrix is non-singular. Then it means A inverse exists, and that means the equation Ax is equal to B can be written as x is equal to A inverse B. That means if we can find out the inverse of the given matrix A, then the solution matrix X can be obtained as A inverse B. So A inverse is to be multiplied by the right hand side and we will get the solution. That means that finding solution of given system means finding inverse of the given matrix, but the inverse may not exist as the matrix may be singular also. So let us discuss a method for finding inverse of given square matrix if it exists. We have already discussed one method of finding inverse, but today here we are discussing a method which uses elementary row operations to obtain the inverse of a matrix. So let us say we have to find the solution of Ax is equal to identity matrix, or we have to find x is equal to A inverse. What we can do is we can apply row transformations. That means we have to find out a matrix P, that is we apply successive row transformation to the system Ax, then Px is equal to I times P or simply P. Now if we apply row operations in such a manner that Pa is equal to I, then x becomes P or it becomes A inverse. So what we do is we apply a row transformation on the augmented matrix A colon I. So instead of having a column matrix B in the case of system of equations, we are having now an identity matrix of appropriate order. We apply row transformations, row operations on A, and we try to reduce this A into identity matrix, and the same operations are applied on I, and we will see that by the time A is transformed into I will be transformed into A inverse. So A inverse becomes P. Now let us illustrate with example. So let us find out the inverse of the matrix, a 3 by 3 matrix as this. Then we consider the augmented matrix as this matrix. On the right hand side will be an identity matrix of order 3. What we have to do is we have to transform this matrix into identity matrix, and by the time it is identity matrix, this will become the inverse of this matrix. Now to convert this into identity matrix, first thing is that this should be 1 and this should be 0. So to perform this, we will write down R2 as 3R2, and then we subtract R2 from R1, and then R3 is 2 times R3. So these transformations give us this matrix. So this is now subtracted. R3 is R3 minus R2, so even this will become 0, and then this has to be made 0 and this has to be made 0. So R2 is 7 times R2 and R3 is 5 times R3, and that will make the two coefficients equal. So when you add the two, this will become 0, and to make it R3 is again 1 by 5 R3, so that becomes 7, and we apply another transformation. R1 is 7 times R1, so that this will become 0. In the next when we add R2 and R1, so this will become 0, and finally R1 and R3 plus R1, so this term will also become 0, and then these have to be made 1, these diagonals have to be 1, so R1 is R1 by 21, R2 is R2 by 14, R3 is R3 by 7, and what we have is an identity matrix here. So we say this is nothing but the inverse of the given matrix. So A inverse is 1 by 7, 1 by 7 I have taken out. So it is 2 1 4 minus 1 3 5 1 minus 3 2 as the inverse of given matrix. So that is how we use row transformations to obtain the inverse of a given matrix. So today viewers, we have seen how to solve system of equations. We have obtained systematic approach for solving system of equations. We have obtained two methods. One is the Gauss elimination method, in which we transform our augmented matrix into a row echelon form, and the other method is Gauss-Jordan elimination method, in which we reduce the augmented matrix into reduced row echelon form. Basically, we have to apply row operations to transform the augmented matrix. This is important because only row operations have to be applied. This gives us a method for solving large system of equations. It is a systematic approach, and these methods can be used for algorithmic development so that the system of equations can be solved with the help of computers. Thank you viewers.
Thank you.